Hello everyone, my name is Liu Rongxuan, and today I'm going to talk about the Lipschitz function and why it implies continuity. It's an important topic in mathematical analysis because it gives us a stronger and more quantitative way to understand the Lipschitz function and the continuous function. First of all, I will introduce the motivation and then introduce the definition of this function and then use the definition to prove the main theory. Why this continuity implies continuity. And finally, I will give two examples and one counterexample to help you understand the Lipschitz function. Motivation continuity tells us that the nearby points have nearby margins, but in the in this continuity, we don't know how fast the function can change. Example like we can change a little or change a very bit fast. Then the uniform condition comes and it provides a uniform bound and the rate of change. This is a formula and I will introduce later. Then the Lipschitz continuity is a stronger form of continuity. Here's a question: does every Lipschitz function have to be continuous? The definition of this function is let D is a subset of Rn and the function is f from D to Rn. This function if there exists a constant L bigger than 0. This means there exists 1. And this formula, this inequality holds for all U and V in D. This means for all means for all points in the domain. And the constant L is called Lipschitz constant. And and if L is between 0 and 1, then we can write this is less than or equal to U minus V. And this is called contraction because it brings points closer and closer. Geometry interpolation. Geometry, the Lipschitz function means that the function cannot stretch distance by more than a fixed factor L. If two input points U and V are close together, then their images f of U and f of V must also remain close. And the output distance is less than or equal to L times the input distance. And the uniform control is the key reason why every Lipschitz function is continuous. The main theorem. The main theorem is every Lipschitz functions are continuous. To prove this, we need to show the definition of continuity. And this means for every point and for every epsilon, and there is this data. And since f is Lipschitz function, then the inequality holds and for all U and V in D in the domain. And we know A is inside D and sigma bigger than 0 is fixed. So we choose data be the epsilon over L. L is a constant from here. And we know already U is in D and the distance between U and A is less than data. So the distance, so we use the definition of Lipschitz function and then the distance between, we know this plug this into here, we get L times data, and then we use data is equal to epsilon over L. Then this is equal to epsilon, and therefore f is continuous at A because this is the definition of continuity at A. Since A is the all points in the domain, so f is continuous on the domain. Why the proof works? Because the constant L controls the rate of change, the behavior of the function everywhere in the domain. So also we can choose the data because there means it says data, so we can choose data to be something. The first example is the same function. Consider the function fx is same as, then we want to show fx is this function. To prove this, we should know the derivative of fx is equal to cosine x, then cosine x, the observed value is less than or equal to 1. So this is less than or equal to 1 by the mean theorem. Since it's one-dimensional, so we can apply the mean value theorem. There is a C, a point C between x and y such that this holds and fx minus fy is uh, we plot this here, then we get is less than or equal to the distance between x and y. Therefore, fx is a function with constant L equal to 1. The second example is linear transformation. Every linear transformation is its function. In linear transformation is Tx equal to Ax, and A is a matrix. To prove this, we need to the Cauchy-Squarge inequality. This inequality is this formula, and we square the absolute value of Az, and then we get this because Ri is the I row of A, and we this is Ri times Z, and we square it. Then we get apply the formula, we get this, and we let a constant square be this, and so we get this. And since C is a constant, so we also we can plug the Z equal to x minus y, then we get this inequality, and this inequality is the definition of Lipschitz function. Therefore, every linear transformation is Lipschitz function. Here's the counterexample. The counterexample is continuous but not Lipschitz function. And we consider if a function f is from 0 to 1, 0 between 1 to r, and fx is equal to the root of fx, the square root of fx, and the function is continuous on 0 and 1. We know it already, and but it's not this function. If it we assume it is a Lipschitz function, then for some constant bigger than 0, we get this. This is a definition. This is a definition of Lipschitz function. We let u equal to 0 and v equal to t. So we got this. And since since u is not equal to v, so t is bigger than 0 and not equal to 0 and less than equal to 1. And switch its position, and we get 1, or we get this inequality. Look here. When t goes to 0, and this is not impossible because we can find a constant bigger than infinite, because when it's going to 0, the shall be going to infinite, so we can find a constant bigger than infinite. Here's the summary. every Lisp function is continuous, and in fact, the same idea also shows uniform continuity, since the choice of data does not depend on the particle point. However, the converse is false. The continuous function, such as square root of x on between 0 and 1, doesn't have to be this function. Okay, thank you. Well, thanks for your listening.